In the last video, we finally started breadboarding and built enough stuff to get something on the screen. We needed the oscillator and divider, the sync counters, the composite output, and we put up the boundaries. Super exciting stuff. Today we'll add the flip logic found on sheet 4. Let's remove these temporary jumpers and add in the flip parts. We'll need the two adders and Nancy 2 and Mary 2. And remember, we're using 74 283s instead of 74 83s, as discussed in the chip challenges section of the first video. While logically equivalent, these are not pin compatible. We'll also need 4 7486 quad exclusive OR gates in Love 2, King 2, Nancy 3, and Mary 3. Flip logic is used when player 2 is up on a cocktail table model. We discussed before that the original drawings were probably made before flip logic was added because of some schematic clues, like signal alignments and the use of prime notation to rename the original counter lines. This is the Rev F schematic as shown in the manual, but I think it was originally like this. Since everything was already drawn, it was probably easier to leave all of the display element signals alone, add a tick to the counter lines, and shove those through new flip logic added to sheet 4. You already know that exclusive OR gates act as signal inverters, so these basically swap each axis's display elements. The prime signals are used when you don't want changes, and the non-prime signals are used for visual elements that can be flipped. One Victor prime is not flipped because it's not used for any visual element. It is required on the input to the adder, however, because it's involved in calculating the proper sum. We created this Visio screen layout diagram in the last session. This shows a normal screen orientation. As you know, the actual monitor is rotated 90 degrees clockwise in the cabinet, and the border signals are named with this rotation in mind. So top boundary is on the left in our drawing, and the sides are on the top and bottom. Our drawing shows the horizontal counters along the top and the vertical counters along the left. The counters 0s and 1s are represented by light and dark boxes respectively. The visual area starts when both counters are at 0 here. You can see the horizontal counter itself starts at 0 and increases to 239 as we sweep out a line in the visual area. H-sync is on when the high-order horizontal counter is all 1s. You can see this represented along the edges here. We also showed that top boundary is only dependent on horizontal signals when 128H, 64H, and 32H are off, and 16H and 8H are on. 4H, 2H, and 1H are not involved in the logic criteria, so the top boundary lands here and is 8 horizontal steps wide. We can call them pixels now because we generate them. You can also see that top boundary is kept out of VSync using this gate. We don't show 1 Henry or 1 Victor on this diagram, mostly because they're not material and there's not much room. 1 Victor is never used for any visual element, and 1 Henry is only used to separate brick layers. We mentioned in the first part that the original prototype had many video issues. If you take a closer look at the drawings, you'll see that the left border is smack up against the beginning of VSync, and the right border actually sits within the end of VSync. There's supposed to be some good neighbor blanking before and after the syncs that's not observed. We call these blanking areas the front and back porches. Let's take a look at this on the scope. I'll first trigger on the fall of VSync. You can clearly see the left boundary just before VSync drops. The side boundaries use 4 whole vertical lines, so the video signal is high for all pixels during the entire last 4 horizontal periods. Let's trigger on the rise of VSync. You can see here that the right side sits inside the end of our VSync signal. But at this point, the vertical retrace is complete, and the right-hand side shows up at the top of the screen. If we consider the right side a shortening of the vertical blanking period, we do get a little closer to the NTSC spec. In the corrected RevFX schematics, we see that these two diodes were added in an engineering change between board revs D and E to keep the left and right sides out of H-Sync. If we temporarily disable this, we can see that the left and right sides bleed into the H-Sync pulses in the composite video, something that evidently needed shoring up before ramping up production. Alright, time to do some flipping. I drew this line along the middle of the horizontal counter bits. It's slightly off-center in the visual space. To flip this axis, we simply invert all of the horizontal signals, so we're basically mirroring the horizontal visual elements about this line. You can see that top boundary now sits here. And we're only showing the top boundary now, but all of the other visual elements make similar horizontal moves when flipped. H-Sync itself doesn't move because it's generated before flipping and is not affected by it. Now the vertical elements are a bit more tricky. They use these adders to adjust the vertical counters before flipping the lines. If we map this out, the flip axis is here. If we just simply invert along this line, you'll see that the visual elements end up in screwy locations. And yes, screwy is a formal technical term. So to fix this, they add 34 to the vertical count before flipping. This moves the flip axis up. It's easier to think of this as starting the visual area at 34 instead of 0. Now when we flip, the visual elements are properly recentered. If you zoom in, however, you'll see that the left and right sides are actually shifted down slightly by 2 lines, and each encroaches VSync. We should see this 2-line deviation if we toggle the flip. Speaking of that, turning flip on or off is controlled by this player 2 conditional line. It goes high when player 2 is up in a cocktail table model. We can tie this up or down for now to test. Fire in the hole. Doesn't look like we screwed anything up. Turn on player 2 conditional. The top boundary moves to the right side as expected. You can also see that the left and right sides shift slightly down when flipped, just like we predicted. Again, not too exciting, but all of the other visual elements come off this logic, so we needed to get it done before building anything else. Let's add this logic to our schematic. We'll make a custom 74283 that resembles the legacy part. Add sheet 4 to our retro schematic. Add the 2 adders. Sounds kind of funny. and drop in 15 exclusive OR gates. They're using that fourth Mary 3 gate somewhere else, which is a shame because we could have added jumpers to completely bypass these 6 chips if you didn't need cocktail model support. The 7486s are cheap, so perhaps we'll just add jumpers to bypass the adders. Don't know yet. Still making this up as I go. While we're in here, we might as well add these pull-ups. And remember, we're going to specifically name these lines per the pull-up resistors, and also use the proper pull-up nets throughout the schematic. For the breadboard, we're just throwing in resistors wherever we need something pulled up to reduce our rat's nest. On the retro board, we'll match the legacy pull-ups and add any pins they left floating. For standard TTL, you can't tie inputs to VCC because it saturates the bipolar base collector junction and drives up the current. Low-powered Schottky inputs have a greater than 7 volt breakdown voltage, so we could tie them directly to VCC, but we'll honor the original approach. We'll use 4.7K resistors instead of 1K, however. These are all static lines, so we can take it easy. For active pull-ups, you can lower the resistance to improve rise time slightly. Looks like a winner. I know we said we'd do the paddle in this video, but it's enough for today. I think we'll get through this whole project faster if we make these shorter and targeted to specific sections. This one was kind of boring, but foundational to most of the rest. In the next video, we'll do that paddle circuitry. Thanks for watching.